Welcome back to our heat transfer class, where we are delving into the phenomenon of the exchange of thermal energy between surfaces by radiation. This video was made with the support of InnoEnergy. After studying the view factors between surfaces, in this lesson we will study radiant energy balances. We will divide this lesson into several parts. The objective is to calculate the radiant flux absorbed and emitted by all the surfaces of a closed enclosure. With this, we will be able to build a mathematical model to predict the heat exchange between surfaces at different temperatures by the mechanism of radiation. Surfaces of an enclosure. In order to fulfill the conservation equation for radiant energy, the first thing is to define an enclosure, that is a closed space delimited by surfaces. Some surfaces will gain heat by radiation. Others will give heat to the enclosure. Others will be insulated. In a closed enclosure, to fulfill the radiant energy conservation equation, the sum of the radiation heat transfer rates for all surfaces must be zero. If the enclosure is not completely closed by physical surfaces, we must close it with auxiliary fictitious surfaces. Let us first define what type of surfaces we are going to consider to build the radiant energy balances in an enclosure. Lambertian surfaces are ideal surfaces of diffuse reflection. For our heat balances, we will also consider surfaces which are isothermal, diffuse, with uniform properties, opaque and with uniform surface flows. Net radiation exchange at a surface. The radiation fluxes in watts per square meter on a surface are irradiation G, which is the incident radiation flux, that is, the radiation that reaches the surface from the outside. A fraction is absorbed, and another fraction is reflected. The emitting or emissive power is the power flow that the surface emits due to its own temperature and that we have learned to calculate in previous lessons. We define as radiosity the radiation flux emerging from the surface. This is the sum of the emitted radiation flux and the reflected radiation flux. The net flux of radiation input minus output will thus be the difference between irradiation and radiosity. In all this set of equations, we have irradiation as unknown. We wonder, how can we calculate it? Radiation exchange between surfaces. We are located on surface 1. The radiation leaving surface 2 is the product of its radiosity times its surface. This radiation is distributed throughout the enclosure. The radiation that leaves surface 2 and falls directly on surface 1 is obtained by multiplying by the view factor 2 to 1. We do the same for the rest of the surfaces of the enclosure. Adding the radiation that arrives from all the surfaces of the enclosure to 1, we have the incident radiation in watts. Dividing by the surface area 1, we have the irradiation in watts per square meter. We divide each term separately by area 1. Thus, we can apply the reciprocity to each term. We group the terms in a summation, and we generalize for any surface. And with it, the net balance of radiant energy on a surface can be expressed only in terms of radiosities. Radiosities method. With these equations we do not have enough to solve the problem. Let us recall the definition of radiosity. It is the sum of the reflected and emitted radiation, and that of the emissive power. Combining these equations, We arrive at an equation where we only have radiosities and temperatures. The mathematical model of the balance of an enclosure is a system of algebraic equations, one for each surface. If we work by bands, there will be a system of equations for each band of the spectrum. Solution when all temperatures are known. Let's start for the case when all surfaces' temperature are known. We first find the view factors between all surfaces. We calculate the radiation functions for each temperature and each band of the spectrum. If all surfaces in the enclosure are gray or black, we can skip this step. We calculate the emissive power for all surfaces. In each band, if there are surfaces with different properties in several bands of the spectrum, we write the system of equations. There will be an equation for each surface, and a system of equations for each band of the spectrum, if needed. We obtain the radiosities by solving the systems of equations. This is the goal of the method of radiosities, to find the radiosity of each and every surface. After the radiosities, we calculate the irradiations. We calculate the net radiation heat transfer rate on each surface. Finally, we check that the sum of radiant heat transfer rates is 0. Remember that for an enclosure where all surfaces are gray or black, NB is 1. When all temperatures are known except for one of them, the solution is different for enclosures where there are surfaces with different properties in different bands, than for enclosures where all surfaces are gray or black. Enclosures with banded gray surfaces. What happens when for a given surface, we do not know its temperature, but the radiation flux? Assume unknown temperatures. In this case, T2. We will use this value to calculate the radiation functions, emissive powers, and radiosities. We will follow the same procedure to calculate the net radiant heat transfer rate. We will be modifying T2 until we achieve the balance of heat transfer rates. Enclosure where all surfaces are gray or black. In these types of enclosures, there is no need to iterate. For surfaces where we know the temperature, we use the radiosity equation. On surfaces where the flux is known, we write the equation for the net radiation flux. The result is a single system of equations from which we obtain the radiosities. Enclosure where all surfaces are black. If all the surfaces are black, the system of equations is simplified. The net flux over each surface depends only on viewing factors and temperatures. Re-radiating surfaces. For a surface on which there is no convection, if it is insulated, the net flux of radiation will be 0. Therefore, the irradiation will be equal to the radiosity. It is shown that, in these cases, the surface temperature can be calculated from the radiosity when the surface is gray.